Dear students, under the lecture series on complex analysis, we are solving problems under the topic Cauchy integral formula. Here we have a significant problem, that is, they are asking us to evaluate the integral over c 4 minus 3z divided by z multiplied with z minus 1, z minus 2 dz, where the circle C is oriented as modulus of z to be equal to 3 by 2. So using this, that is using Cauchy integral formula, we have to evaluate this integral. So for that, first of all, we have to rewrite this given integral in the form where we can apply the Cauchy integral formula. That is, we have to rewrite it in the form integral over c f of z by z minus z naught dz. Now since we have product of three terms in the denominator, we have to split it by using partial fraction. So let us first split the denominators by using partial fraction. That is, we will write the denominator, that is 1 by z multiplied with z minus 1, z minus 2. So this can be written as a by z plus b by z minus 1 plus c by z minus 2. Now we have to apply, that is, we have applied partial fraction over here. So from this we get 1 to be equal to a multiplied with z minus 1 multiplied with z minus 2. So this is by the method of partial fraction, plus b multiplied with the other two, z and z minus 2, plus c multiplied with z and z minus 1. Now we have to find the value of a, b and c. So first let us put z to be equal to 1. So when you put z as 1, so we will be getting this left hand side is 1 equal to. So when you put z as 1 over here, 1 minus 1 becomes 0. So this term becomes 0. And here you will be having b multiplied with 1 multiplied with 1 minus 2 is minus 1. And here when you put 1, this also becomes 0. So from this we obtain the value of b to be equal to minus 1. Next we shall put z is equal to 2. So when you put z as 2, we get 1 to be equal to. So when you put z as 2, this term also becomes 0. Here when you put z as 2, this also becomes 0 because 2 minus 2 is 0. Now here when you put z as 2, we get c multiplied with 2 multiplied with 2 minus 1 is 1. And therefore we get the value of c to be equal to 1 by 2. Now in order to find the value of a, we have to put z is equal to 0 because we have z over here. So when you put z as 0, we will be getting 1 to be equal to a multiplied with. So if you put z as 0, here you will have 0 minus 1, which is minus 1. And here you will have 0 minus 2, which is minus 2. And the other two terms become 0 because when you apply z as 0 over here, this term and this term as a whole becomes 0. And from this, minus into minus will become plus, and the value of a we will obtain to be 1 by 2. So these are the values of a, b and c. A is 1 by 2, b is minus 1 and c is 1 by 2. So substituting all these values of a, b and c over here, we get 1 by z multiplied with z minus 1 multiplied with z minus 2 to be equal to. What is a? A is 1 by 2. So 1 by 2 multiplied with 1 by z. And then b is minus 1. So minus 1 by z minus 1. And c is 1 by 2. So when you put that as 1 by 2, we get 1 by 2 multiplied with 1 by z minus 2. Now we shall make use of this in our required integral. So instead of 1 by z, z minus 1, z minus 2, we will split up this one integral into three different integrals with these. So therefore what we get is integral over c 4 minus 3 is it the required integral divided by z multiplied with z minus 1, z minus 2 dz to be equal to. Now we shall apply this to each of these. So this 1 by z, z minus 1, z minus 2 transforms as like this. Like for example, for the first integral, 1 by 2 is a constant, integral over c, and we have 4 minus 3 is z, and here we have z, d is z. Similarly, then here minus integral over c. So what is the numerator here? 4 minus 3 is z divided by the second integral. Here we have z minus 1, d is z. And then finally with this. So plus 1 by 2 integral over c. We have 4 minus 3 is z divided by z minus 2, d is z. Now we have to evaluate each of these integrals separately by applying Cauchy integral formula, because we have rewritten this integral into three different integrals where each of the integrals can be easily found by applying the Cauchy integral formula. So we will find one by one. So in order to apply the Cauchy integral formula, first we have to check with f of z. So what is f of z over here? F of z is 4 minus 3 z. We know that constant function is always analytic, and also a polynomial minus 3z is also analytic, and the linear combination of these two will surely be analytic. Therefore, from this we say that f of z is analytic inside and on C. So now we are done with the first condition. The second condition is, for each of the integrals we have to check whether z naught lies inside C. For that, first we should see what is the given circle C. The circle is at the origin. So this that is the center is at the origin, and the radius is equal to 3 by 2. So that is equal to 1.5. So we are considering a circle which has the center at the origin and the radius is 1.5. Now we have to check whether for each of the integral z naught lies inside or outside this circle. So if it lies inside the circle, we apply Cauchy integral formula. If it lies outside the circle, by Cauchy's theorem, that integral becomes 0. So let us check for each of the integrals. So in the first integral, we have z minus z naught, that is z naught is 0. So z is equal to z minus z naught. So from this what we get, z naught to be equal to 0. Now we should check whether z naught lies inside or outside the circle. We know that the circle is modulus of z is equal to 1.5. Now let us check that. From this, what is modulus of z naught? It is equal to 0 only. And 0 is obviously lesser than 1.5. So we can say that z naught equal to 0 lies inside the circle C, because the radius is 1.5 and we have modulus of z naught to be 0, which is lesser than 1.5. For the second integral, we have z minus 1. So we will write it as z minus z naught. So on comparing, what do you get? Z naught to be 1. Now we will check modulus of z naught. So that will be equal to modulus of 1, which is equal to 1 only. And 1 is lesser than 1.5. So from this we can say that z naught equal to 1 lies inside C. So for this also, for this and this, z naught lies inside C only. And the third integral is z minus 2, that we will check now. So z minus 2, which is z minus z naught. So from this we get z naught to be equal to 2. What is modulus of z naught? It is equal to modulus of 2, which is 2 only. But 2 is greater than 1.5, which means it lies outside the circle. So therefore, z naught equal to 2 lies outside the circle C. So we see that for these two we can apply Cauchy integral formula and we can evaluate those two integrals, that is this and this. Whereas the third integral, since it lies outside C, it will become 0. So now let us evaluate each of these integrals. So therefore this will be equal to 1 by 2. So let me write it. So if you see here, so this integral I have written is equal to this 1 by 2 I will write. Now what is integral over C 4 minus 3z by z dz? We can apply Cauchy integral formula. It will be 2 pi I multiplied with f of z naught. Z naught here is 0. So f of 0. And then minus, what about this integral? This also z naught lies inside the circle. Therefore, we can apply the Cauchy integral formula. So here we will be having 2 pi I f of, here z naught is 1. So f of 1. And here we saw that here z naught lies outside, therefore this integral was 0. So plus 1 by 2 into 0. So therefore we obtain this to be equal to, so this 2 and 2 gets cancelled, pi I multiplied with f of 0. Now what is f of z? So from the question, f of z is 4 minus 3z. So f of z is 4 minus 3z. This only we had shown to be analytic. So now f of z is 4 minus 3z. Now here we have f of 0. So at the place of z we have to put 0. So this becomes 0 and so we multiply this by 4 minus 2 pi I multiplied with f of 1. So if you put z as 1, 4 minus 3 we will have, which is 1. So this is equal to 4 pi I minus 2 pi I. What is 4 pi I minus 2 pi I? It is 2 pi I. Therefore, we have evaluated the given integral to be equal to 2 pi I. Hence, by applying the Cauchy integral formula, we have evaluated the required integral. In our upcoming video lectures, we will solve problems under higher derivatives and the application of Cauchy integral formula in them. So, kindly follow the upcoming video lecture for problems under higher derivatives. Thank you.